so-called Schoenflies classification, but as I was looking at this, I admired the size of this group, which is called the largest group, largest of the exceptional groups, because there are infinite ones which are classified, like the cyclic group of prime order. So those are of course there, but if you look at this, this is the so this actually also tells you perhaps the cycle structure, 2 to the 46, 3 to the 20, 5 to the 9. So it is some number. But the thing to remember is that even this is embedded in a symmetric group, in a permutation group whose size is this many factorial. Okay. So even this group is embedded somewhere in some symmetric group. So that's nice to know. So by the way, I have been reading quite a lot about this, because not about this particular thing, but group theory. To teach you, I have been studying a lot, and I am realizing that in the last 25 years or so, there has been such great flowering of this whole technique. Not that group theory was not known. Group theory was known to mathematicians for a long time. The theorems are all from 19th century. But its application in physics was just taking off in the 1960s, 70s with infrared spectroscopy, Raman spectroscopy, some few rudimentary, spectroscopies. But in just the last 25, 30 years, it has really undergone an exponential growth in the techniques that can detect all kinds of, and the material science has grown. So all these methods, the way they are being applied to physics and to chemistry. And the other thing is, I hope no chemists mind my saying this, but when we were learning chemistry, it was all about, color, smell, and what mineral it comes from and all this. But now chemistry has actually become a physical science with understanding in terms of the molecular bonds, and which ultimately boils down to quantum mechanics and symmetry. So that kind of understanding of chemistry has also grown by leaps and bounds, so that there are lots of sources now available which clarify all of this quite well. So that is why I am probably finding it difficult to teach all of this, because suddenly there has been such a great growth and lot of things I didn't know have come around. And so I hope that you will understand that although it sounds like a very old subject, it's really from the physics and the sciences point of view, it is a subject undergoing a great growth still. A lot of things are happening in it. And you may know the story of DNA discovery, where this was 1953 or so. The two physicists, Crick and Watson, the biologists were taking the X-ray crystallographs of the molecules and storing them and trying to study them. But Crick and Watson kind of spied on somebody else's lab, biologist's lab, understood that the crystallograph represented the double helix. I think the crucial thing was also the hydrogen bond between the spirals, and they understood the presence of all this, and they were able to crack the code. So ever since then, X-ray crystallography is very, very important also to all the biological sciences. So all of this is growing very rapidly, and we will just try to do the basics and the basic ideas of how it can be applied. So towards that, we will focus more on the molecular groups and what is called Schoenflies classification, although Schoenflies is also from turn of 1900s, from 1800 something to 1900. But this is the notation known after him, and then there is another one which is used for crystallography. So we will not get into that, because to get into it you have to actually start understanding crystals and start understanding other physical effects which are not part of this course. So to just illustrate how this mathematics can be used, we will apply to the simplest and more obvious systems. So so to begin with this classification, as I have written here, there are three broad categories in which the group theory is applied. One is the molecular groups, where there are shapes of finite size with a fixed center, and the other are lattice groups, which are space filling, but you try to map out the symmetries of their unit cell, but the translation invariance goes with it. So the entire group of symmetries actually consists of the product of both and the translations are also along fixed lattice directions. So those lattice vector translations, and also there are some screw shift symmetries and so on. It gets much more complicated and interesting if you are studying those systems, but we will confine one thing I want to mention here among the lattice groups. So it turns out that because of this fact of having to have translation invariance, the symmetries of the unit cell have to be such that they are compatible with translations. So they have to be space filling. So this puts a restriction on the number of groups you can have, number of molecular kind of groups you can have in a lattice. So for example, in the plane, you can only have 2-fold, 4-fold or 6-fold symmetry, because with a square or a hexagon you can fill the two-dimensional plane. But with say pentagon, you can't really be, I mean that's what people thought, you can't be filling the space. And with other shapes you can't. A surprising discovery in the 1960s was that actually there were crystallographs that showed pentagonal symmetry in a space filling way. And everybody thought that the guy was a crackpot. Eventually got Nobel Prize about 5 years ago for discovering this. And the solution was that the pentagonal symmetry existed, but there was no translation invariance really. There was approximate translation invariance. You can't really fill it in a symmetrical way. So actually it's a never repeating pattern in a sense. If you just kept extending it, you can keep filling the space where every one of the nodes will have pentagonal symmetry around it, but the pattern as a whole does not have translation symmetry. It has approximate translation vectors which have to be kept modifying as you go further away. So that was a very interesting discovery of a group that is not quite a lattice group, but it is a space filling pentagonal symmetry. And apparently it was there in M.C. Escher's paint. You know M.C. Escher's painting? Escher, E-S-C-H-E-R. If not, you Yes, yes. Correct. So you should look up M.C. Escher's graphic art. So some of the space filling pentagonal things are there in it, but they don't become, there is no translation invariance in 5 directions as such. Okay. So now as far as this, let me actually switch here for a moment. I was about to say symmetries in physical systems, but that would be too vast. So molecules and lattices, and we will focus on molecules. So here I want to say something that I found that is kind of missing in many textbooks, which most diligent students will learn without being told, but because I like to say things more clearly. There is a redundancy of notation. There is a set of symbols for symmetry elements, and then there is a set of symbols for symmetry groups. By Cn, they mean an n-fold symmetry axis, no surprise. Then they have a symbol I, which is space inversion. where you send each of the three axes into negative of themselves, x go to minus x, y go to minus y, z go to minus z. And then there are symmetry elements called sigma v. So sigmas refer to some planes usually. So C refers to axis, sigma refers to a plane. This is typically a plane that contains the Cn axis. And then there are sigma h is horizontal, so which is usually perpendicular to the Cn axis. There are a couple of more things. There is also sigma d, dihedral plane, we are just within the writing, which usually bisects two of the CV planes. Bisect the angle between sigma v planes, I am sorry. There will be this notation C2 prime or Cn prime, usually only C2 prime, which are some kind of supplementary axes. They are not like the main z axis, but axes that are perpendicular to it. So if you think of benzene, you have a 6-fold symmetry axis passing through the center, but then through in the plane you have three other axes available around which you can flip the whole molecule, the plane, turn it around, usually a C2 axis, but they put a prime on it just to show that it's a minor one, it's not the major one. So less important, okay, not minor in any other sense. Finally, I am sorry I have packed it up like this, but maybe it is now becoming a 2-column format. There is something called Sn, which is Cn necessarily combined with an improper rotation, Cn combined with mirror reflection. So this is when you have staggered configuration. I will show you, we will come to this, okay. Combined with what they call improper rotation, so it's a mirror reflection. Okay. So that is about symmetry elements. Now you will find that there are various groups listed by identifying these elements. So you take a molecule and then you say, does it have a Cn, does it have a CH, sigma H, does it have a sigma V, etc. Then you decide, oh yes, my group is Cn. It's the same symbol used, but now it is meant to denote the group. Okay, it's essentially the cyclic group of order n. Then you designate things called CV, CNV, that is Cn with n symmetry planes, n reflection planes containing the axis. So this we had written somewhere, isn't it? So here you can see we have written down the classification for molecular groups. The CN groups are with a redundancy of notation. CN groups are those that contain a CN axis. I hope you will not get confused, and all the chemistry books write this without even bothering to tell you that the same symbol is being repeated, but so that's what it is. So CN basically has 2 pi by n fold axis of rotation. Usually it is denoted the z axis, and most books just assume it has to be z, no, what else can it be. Then CNV is the set of groups, class of groups which have CN rotation axis, that is 2 pi by n rotation axis, and reflection planes containing the axis of rotation. These are YZ or XZ planes. These are planes that will usually contain Z axis definitely, because it is V sigma, it's a sigma V element which contains that axis. Could be YZ and ZX, it could be even other planes. Then CNH are things with this 2 pi n rotation axis, but a reflection plane perpendicular to axis of rotation. So it has same structure above and below. We will see some example of this. In this case, it is since it is perpendicular to the axis of rotation, it should be XY plane, not XZ. This is an error I have to correct. Then come the class of things called DN, and the DN are essentially molecules that have two-fold symmetry in the plane perpendicular to the axis of rotation. So maybe I will come to the pictures right away. We'll just finish saying this and then you will see. D is for dihedral, and then additional D and H are additionally reflection planes that contain axis of symmetry, but which also have planes bisecting the angle. So they have this element sigma V as well as sigma H. So sorry, sigma H as well as sigma D. So we will come to these. And there is Sn, which include the improper rotation. So the same symbol Sn is used for a group element as for the group entirely that consists only of Sns. And when writing Sn, it is emphasized repeatedly, if it is possible to get away with n-fold rotation alone without reflection, then it has to be called Cn. These are special things where you rotate, but there is a staggered symmetry, so that after rotating you must also reflect to recover the molecule. So we will see the examples now, and for this I have downloaded a nice presentation from a German university. So this is, as you see, 31 slide PDF, but actually each slide contains 2 of his PPT slides. So it's about 60 plus slides, and it is a complete crash course on everything we are going to do. Not everything, but most of it. So since it is an opportunity to go over some of the more important things, let me just show that. So he has quoted Eugene Wigner, who was one of the pioneers of, in fact the pioneer of applying group theory to physics, including molecular symmetry, relativistic invariance everywhere. Wigner worked out the symmetry groups and their representations and etc. And Wigner also seems to have remarked at some point that this is unreasonable applicability of mathematics to physics, that so much physics would be explicated by application of 19th century mathematics was completely unexpected. So he calls group theory the unexpected applicability of mathematics to physics. So here is the list of his thing. This is a space filling group, but this has translation invariance as well. But there is additionally coloring, so it is called some wallpaper group. We are not going to do that. He has given various kinds of links to outside sources, so you can you don't have to judge me because he also uses other links, so I use his link. This is a nice example of what we are not going to do, and since we are not going to do, I may as well show this transparency nicely. You can read all this text because I will put it up or give a link to this, but main point is they have now discovered a gold 20 configuration. 20 atoms of gold form themselves into a little pyramid like this, and so here is the Raman spectrum corresponding to it, and because of the high degree of symmetry you get a very sharp peak because there is a huge degeneracy of levels that do this. And here to show off they have their theoretical calculations which exactly match it. And then you create, of course it is done, there is some detail here, there is some krypton added to stabilize it or something like that, but apparently it does not affect this symmetry. Then they work out, they claim that actually energetically more favorable is gold 19, not gold 20, where you chop off this top and then you are left with a truncated pyramid. When you truncate it, the degeneracy of these levels breaks and some of the levels shift in frequency. So you get a shift in the frequency. Actually here, these are the ones with red dots are the experimental data, and they get a peak over here there, which they are able to reproduce exactly if they assume that this is what happened. So symmetry can be used to exactly fit the you can get the relative height of the peaks from this as well, from group theory as well, because the multiplicity of levels that will give this transition versus this, that ratio will be the ratio of the, at least the amplitudes of these, if not the intensity. Okay, so that is one of the uses. And similarly here, this diagram is bit difficult to look at first, but roughly speaking what it shows is that whether you include certain symmetries or not, let me leave it at that, but you can see a coincidence of, this is from condensed matter physics. The x-axis, the y-axis is energy in Rydberg of the level, it is a band structure, and the band is dependent on the momentum vector, the wave vector k, wave number vector. So x-axis is wave number vector, and there is a unit lattice, so that k has a finite length, I mean the values. There is a particular one where there is a coincidence of lot of levels coming together, and that also has to do with group theory, and you can deduce it from the group embedding of that unit cell, the symmetry of that unit cell. So there is long list of literature. Then there is early part of the group theory discussion which you can read for revision if you like, but I want to focus on, yes, classification of point groups. So begins with saying there are groups C1, Cs and Ci. As I said, there is going to be a redundancy in what is meant by an element of the symmetry operations and a whole group. So C1 basically has no symmetries, and Cs essentially has only a mirror plane and nothing else. So I think in this example there are these two, so this has no symmetries at all, I think this is C1. And then there is mirror plane which exists in the case of this molecule because it is planar, but it has no other rotational symmetries because of this red thing added on. Then we come to, so there is this three categories of, and Ci, I is the inversion element, so space inversion is included, but there is nothing else possible. So that is, these are the simplest, very trivial groups. This has only one element and these two have two elements each. Then we come to the bigger groups. So Cn, as we have been saying, contain the identity element and the 2 pi band rotation axis, and you from the, so you can understand what I was trying to tell you. The group is called Cn, but then here this Cn means the Cn axis, okay, and the Cn axis, one rotation squared gives you Cn square, Cn cube and Cn to the power n minus 1. These are n-fold rotations. So these are elements of that symmetry. Raised to power n you will return to E. So CN group will contain a CN axis, sorry for the redundancy, that CN axis rotation done n times brings you back to identity. So in this line the CN refers to the group element, here it refers to the group itself. And the example that he has chosen is H2O2 hydrogen peroxide. It's not shown here, it's a non-planar molecule. So you can rotate it twofold only, it's like an armchair, so you can rotate it twofold. Okay, now come the SN group, which is what I was telling you, you have to be careful. Contains E and only an improper rotation. If it contains proper rotations, usual CN rotations, then you have to classify it with this, or there are other classifications. Those things that have identity element and only improper rotations by 2 pi by n are called SN, and you can imagine that axis is called SN axis. And the example is this tetrafluorocyclooctatetraene. Okay, I said it. If you look at this picture a little carefully, what it is trying to show is that this green and this green are coming out of the plane, and this green and this green are dipped below the plane. So there is this octagonal planar system, and then these two greens are attached to it coming out of the plane, and these two are attached going into the plane, and similarly 2 of the whites come out of the plane and 2 of the whites go into the plane, and that thing is shown in side view over here, but it is not also immediately very clear, but that's what 2 of the greens come out, the ones that are opposite, they come out of the plane, and 2 of the greens go below the plane. Similarly 2 whites are out, and so now you can see that I can rotate this group by this molecule by 90 degrees, that will bring this green over here, but it will still be above the plane. So to get to the original configuration I have to flip it in the plane containing that octagonal ring. So this is exactly an example of an S4. So this is a good example, and incidentally from reading other I've read lots of them. Reading another transparency, I know that in fact this comes in 2 configurations. This is called boat, and there is another one where this these 2 are flipped up and down, and it's called a chair. So there 2 nearby ones will be above and 2 nearby ones will be below. That becomes like an armchair. This is where they are like this, and it's called boat. Okay, now we come to this nomenclature C and V, which is very frequent, as he says. It contains identity Cn and n mirror planes sigma V. So sigma V are planes which contain the Cn axis. The simplest is this ammonia molecule, where you of course have this axis vertically, about which you can rotate 2 pi by 3 at a time, but then you can draw a plane which passes one of the hydrogens and then the nitrogen, or this hydrogen and this nitrogen, or this hydrogen and this nitrogen. In fact, he calls them sigma V prime and sigma V double prime axes. Okay, the one containing identity is probably left out. So sigma V prime, and so again these primes are used just to indicate that they are somewhat of less important elements, or that there is a multiplicity of them. So sorry, this is anyway C2V, this is C3V, I don't know why, so he has not written out C3V. C3V would contain, this is C3V, it would contain C3, and it would contain sigma V prime, sigma V double prime, and a sigma V triple prime, so should not be left out. Okay. Then there are the CNH groups which contain Cn, so it contains this, but H means a sigma H plane, a horizontal plane. The rotation axis corresponding to Cn with largest n is always taken as vertical, so Z axis, vertical is obviously Z, right. For n even, an inversion center also exists. So here there is so this is the hydrogen peroxide molecule. No, this is not hydrogen peroxide. Oh, it is written plain. So this is the planar version, but on Wikipedia when I read hydrogen peroxide, it said both in gaseous and in its crystalline form, it is essentially a non-planar molecule. Anyway, we can take this whatever is drawn here for the time being, where these pink ones which are hydrogens and the big red ones which are oxygen are all in one plane, but they are staggered. This is here, that goes back, then this red comes forward and this pink goes back. You can see that this has a sigma 2 plane, you can rotate it by sigma 2, but it does not contain a vertical symmetry axis, right. So the z axis in this case runs like this, it runs perpendicular to the plane of the molecule. You can do a sigma 2 rotation, but there is no C2V plane because there is no symmetry plane passing through this axis. However, there is a plane containing the whole molecule, which is a horizontal sigma h plane, and therefore it would be sigma 2h. In fact, if we go to that site Otterbein, it will show all this along with animations. Okay, so sigma, then the group Dn. So Dn contain E, Cn, and then there is a prime which is not visible here, n number of C2 prime. Can you read this? You can read it, right? So n number of C2 prime axes which are normal to the Cn. So this is a Dn but with a D. There is no simple example of a Dn given, but you get the idea. Well, you can just think of a cube, then it has fourfold symmetry axis, and then the plane perpendicular to this axis contains at least 1, 2, 3 and 4 perpendicular to it, where you can flip the whole. So don't make it a parallelepiped so that there is no other symmetry. So there are two squares and there is a long side to it, a box like this, but you can flip the whole box by 180 degrees. But there are 1, 2, 3 and 4 independent axes available for flipping. So that would become a D4. It would have C4 and then 4 C2 prime axis perpendicular to the C4, that would make a D4 group. Then the D and D group, which contains this C2 prime axis and mirror plane sigma D, which bisect the angles between the C2 prime axes. So this prime is missing here, which bisect the angles between the C2 prime axes. If n is odd, then there is also an inversion center. So we can look at this molecule which has a triangular configuration like this, which is not planar by the way, although these three are in a plane. The black one is not in the same plane as these pink ones. There is further back is black one, and then there are 3 pink ones which are again out of that plane, but the 3 pink ones are in a plane. Now if you compare the location of this triangle with the triangle in the back, the two triangles are staggered by 30 degrees, so that this apex, if you project it downward, will fall in between these. So this satisfies these criteria, that you have firstly drawing z axis through this, you have a 3-fold symmetry because you can keep rotating, this one will it will come back to itself. You do have 3 C2 axes which are normal to it. So you can n number of C2 axes normal to Cn. You can draw an axis passing through along say this pink and this black direction, this pink and this black, and this pink and this black. Those are equivalent to drawing also through this pink or this black. So there are 3 independent axes which are perpendicular to this z axis, around which you can do 120 degree rotations, and you will know that actually it will not come back to itself. This will come in a staggered position, D and a sigma D, right. So this is n C2 prime axis normal to Cn. This doesn't have that, because a 180 degree rotation will bring this pink to a staggered position here. So I have a problem with this. Okay. In any case, if it is meant to give the example of dihedral plane, that is what is the important thing. So we draw these C2 axes which are perpendicular. In between them are, so there is a reflection plane which contains the z axis and which bisects this axis and this, the rotation axis about this and rotation axis about this. Isn't this correct that this is not a C, those axes are not C2 axes, but there is certainly a dihedral plane which is in between these two, which is a symmetry. So there is a dihedral plane that bisects the angles between the C2 axes. And then D and H, these contain E, and there is, if n is odd, there is also an inversion center, because you can see that if you are sitting in the center of this rod, which is the z axis symmetry axis, and if you do a space inversion, this pink will go into that pink and this pink will get flipped into that pink. So there is a space inversion symmetry present whenever you have odd number of these. Then D and H, H obviously means there is some sigma H plane. So it contains E, Cn and C2 prime axis normal to Cn and one horizontal mirror plane. For even n, there is also an inversion center, and then there are n by 2 mirror plane sigma d which bisects the angles between the C2 prime. So this is a little better, the so called eclipsed ethane, these pinks are in corresponding positions. Okay, so if I flip, I have a mirror plane, and if I flip, I will get this to go to that, this to go to that, that. So this is quite clear. It actually fits our this criteria, so forget the D right now, so C and H, and then there are mirror planes passing through this pink and the two blacks which will be extending like this, so that exchanges these. So, and there are 3 such mirror planes. So there are n by 2 mirror planes sigma d which bisect the angles between the C2 prime axes, and n minus 2 mirror planes that contain the C2 prime axis. So the C2 prime axis, if you are drawing them like this, then there are mirrors containing them as well and mirrors that bisect them also. So for n odd, there are n mirror planes that contain the C2 prime axes. So if n is even, then you have both types. If n is odd, then you get only the containing C2 axes. Now come the so called special groups. We are not going to use these too much, but just to complete, just for completeness and understanding, you do have these very highly symmetrical things where you have just a 2 atom biatomic molecule. Okay. So if the atoms are unequal, then you firstly have a C infinity axis, because you can of course rotate by any infinitesimal angle as well. So about this z axis there is a continuous set of rotations possible, so it is called C infinity axis. And then there are CV, infinite number of CV planes, because you can draw all kinds of planes that contain the 2 molecules and rotate. So there is infinity of planes containing the z axis, and that is in a sense the symmetry group of the cone, heteronuclear diatomic molecules, and the other example being a cone. You in fact have a higher symmetry, d sigma h. So d, because now there is a plane cutting this axis around which you can mirror reflect, and you have the same thing, that is the homonuclear diatomic molecule. It has all the symmetries that are symmetries of a cylinder, a C infinity axis and infinite number of CV planes as well as a horizontal axis. Then come the special groups. So the special groups, and they are not directly useful because nothing in nature comes that highly symmetric. But of course ammonia is almost close to being this. Ammonia is this, it has this symmetry T, it has 24 elements. And then the cube, group of the cube, and the group of the other platonic solids, there are totally only 5 as you know, the only 5 possible regular polyhedra, and there are groups of those. This C60, the carbon molecule, became very important, fullerene, so these symmetry groups would be useful there. And finally, we end this part of the talk by having the comprehensive list. So, this particular page 16, lower half of the slide, page 16 contains 2 slides, no 15, so 16, yeah 16, yeah, that's right. So, 16 is the key slide to look at. It has 2 slides, 2 PPT slides in it, one which has a complete list of all the groups that we discussed. Okay. The non-axial groups CN, CS, CI, then the CN groups which are just rotations, DN groups that have perpendicular planes, CNV that have planes containing the rotation axis, CNH which have horizontal axis of symmetry and dihedral symmetry, probably CNH is. So, you can look at this table, and this is all there is to know about molecular groups, and the SN groups which require necessarily a mirror reflection, the cubic groups which mostly take care of all the they have not listed probably the higher groups because they probably are composite of the previous groups, and then the linear groups that we just showed that occur for diatomic molecules. So, this is basically it. And so, it is worth looking at this, and as he points out, Jacobs University DE also contains all the group theory information. So, 2 websites I will really recommend is this Jacobs, because it has all the character tables which we will be using later or you may want to use ever, and the other is this Otterbein which has nice simulations. Otterbein is in the US, I think near Ohio State University, and this Jacobs is in Germany.